You know, black holes are these bizarre places where the laws of physics as we know them just totally fall apart. They are these cosmic monsters, so incredibly dense that nothing, not even light itself, can escape their pull. They are the ultimate end for the biggest stars, and maybe, just maybe, the ultimate fate of our entire universe.
So, that's what we're going to get into. We're going to tackle the big questions, right? We're going to follow their whole life story, from their super violent birth to their impossibly, mind-bogglingly slow death. And yeah, we are absolutely going to explore that terrifying question. What would actually happen if you fell in?
All right, so to really get where a black hole comes from, we've got to go back to the beginning. We have to talk about its parent, a star.
So what is a star, really? Well, at its heart, it's basically a giant cosmic engine. It's this massive ball of hydrogen that's collapsed under its own gravity, and it gets so dense and so hot that its core just ignites with nuclear fusion. This process literally crushes hydrogen atoms into helium, unleashing an amount of energy equal to billions of nuclear bombs going off every single second.
And this right here, this is the story of a star's entire life. It's this epic tug-of-war. For billions of years, you have the outward push of all that energy from fusion in a perfect, delicate balance with the inward crush of gravity. And as long as that fusion keeps chugging along, the star stays nice and stable.
But, you know, for the really big stars, this delicate balance, it's not going to last forever. It's doomed to fail. And when it does, the end is one of the most violent events in the entire cosmos.
See, as these huge stars get older, their cores get hotter and hotter. They start fusing heavier and heavier elements, from helium to carbon, then all the way up the chain to iron. But iron is a game changer. Fusing iron doesn't release energy. It actually sucks energy in. The star's engine suddenly and catastrophically runs out of fuel.
And then it all happens in the blink of an eye. The iron core hits a critical point. That outward radiation pressure just vanishes, and gravity wins, decisively. The core collapses in a fraction of a second, imploding at nearly a quarter of the speed of light. This triggers a cataclysmic supernova explosion. And if that original star was big enough, the core just keeps on collapsing into a black hole.
And boom, just like that, our monster's born. So what is a black hole really? Let's kind of break down its two main parts.
Okay, first up, you've got the event horizon. This is what you would actually see, this perfect sphere of pure blackness. Now, it's not a hard surface or anything. It's more like an information boundary, a point of no return. Once anything crosses it, it's never coming back out, because to get out, you'd have to go faster than the speed of light, and, well, that's impossible.
Right, so if the event horizon is the black part of the black hole, then the singularity is the whole part. It's this point at the very center where all the star's old mass gets crushed down into a single point with, theoretically, infinite density and zero volume. And honestly, we have no idea what it really is. Our laws of physics just completely break down here. It's like the universe trying to divide by zero.
And let's just get one thing straight, a really common myth. Black holes do not suck things up like a cosmic vacuum cleaner. Their gravity is only super extreme when you get really, really close. I mean, if we swapped out our sun right now with a black hole of the exact same mass, Earth's orbit wouldn't change one bit. We just, all freeze to death. So they don't suck, they just have gravity, like everything else.
All right, now for the part you've probably been waiting for. What if we ignored every single warning sign and decided to, jump into one?
This is where things get super, super weird. It's all because time gets warped. So, to your friends watching from a safe distance, you would appear to slow down as you get closer to the event horizon. You'd get redder and dimmer until you seem to freeze in time right at the edge and then just fade away. But for you, from your perspective, you'd watch the entire future of the universe flash before your eyes.
So once you cross that event horizon, we think one of two things happens. The first one has the best name, spaghettification. The gravity at your feet would be so much stronger than the gravity at your head that it would literally stretch you. You'd be pulled apart, atom by atom, into a hot stream of plasma just one single atom wide. The second option, which is a lot more controversial, is the firewall theory. Some physicists think that the moment you hit the event horizon, you just slam into a wall of high-energy particles and be instantly incinerated. This idea is still really hotly debated, but either way you slice it, it is not a pleasant trip.
Now, how fast this all happens to you really depends on the size of the black hole you pick. With a small stellar mass black hole, the gravity changes so steeply that you'd be spaghettified before you even reach the event horizon. But with a supermassive one, it's so huge that the change in gravity is much more gentle. You could actually cross the event horizon and survive. For a little while anyway.
And when we say supermassive, we are not kidding. The current heavyweight champion of the universe is a black hole called S50014+81. And this thing is a staggering 40 billion times more massive than our Sun.
To try and put that into perspective, its diameter is 47 times the distance from our Sun all the way out to Pluto. It is just incomprehensibly vast.
But believe it or not, there's a final twist in this story. Even these cosmic titans, these absolute monsters, they don't live forever. They will die. And not with a collapse, but with a final, massive explosion.
This happens through a process called Hawking radiation, and it's pretty wild. It turns out that empty space isn't really empty. It's constantly fizzing with these little pairs of virtual particles that pop into existence and then immediately annihilate each other. But if this happens right on the edge of an event horizon, one particle can fall in while the other one escapes. That escaping particle becomes real, and it takes a tiny, tiny bit of the black hole's mass energy with it.
Now, this whole evaporation thing is incredibly slow at first, but man, does it pick up steam as the black hole gets smaller. When it shrinks to the mass of an asteroid, it's radiating at about room temperature. By the time it's the mass of a mountain, it's glowing as hot as our Sun, and in its final second of life, it explodes with the energy of billions of nuclear weapons.
But don't wait up. For the biggest supermassive black holes, this evaporation is going to take a Google years. That's a 1 with 100 zeros after it. It's a stretch of time so vast, it makes the current age of the universe look like the blink of an eye.
And that leads to a pretty heavy final thought. By the time the last black hole finally explodes and radiates away into nothing, the universe is going to be a cold, dark, and empty place. The era of stars and planets and life will be a distant, long-forgotten memory. There will be absolutely no one left to see it go.
And all of this leaves us with one of the biggest head-scratchers in all of physics, the black hole information paradox. See, one of the fundamental laws of the universe says that information can never truly be destroyed, but a black hole seems to just delete everything that falls into it. So where does all that information go? It's a question that physicists are still battling over to this day.